Okay, so get ready because today we're talking about big numbers, like really big.
Yeah, we're going to be diving into the world of infinity.
Exactly.
And I got to warn you, it's going to get pretty mind-bending.
Things are about to get weird.
Yeah,
We're
right.
taking inspiration from a Vsauce video about the biggest number, but
Our goal isn't just to find some massive numerical behemoth.
right. We want to understand how mathematicians think about this concept of infinity.
It's less about pinpointing a specific number
Yeah,
and more about exploring this idea of endlessness itself
right.
and the surprising ways we can categorize it.
So the video kicks off with a pretty interesting example. It
Yeah.
says the biggest number on Earth, like physically speaking, is 40.
Really?
Turns out there's this giant 40 made of trees
Wow.
somewhere in Russia. I mean,
That's a great illustration of how the idea of biggest can be surprisingly subjective.
so it's less about the actual value of the number and more about how much space it takes up in the real world.
Exactly.
Exactly.
But to really dive into the realm of big numbers, we need to talk about two key types of numbers, cardinal and ordinal.
When I hear cardinal and ordinal, I think more about birds and church rankings than math.
Think of it this way. Cardinal numbers are all about counting,
Okay,
like how many apples are in a basket.
gotcha.
Ordinal numbers, on the other hand, are about position or rank,
Okay,
like who came in first, second, or third in a race.
makes sense. So cardinal is how many,
Yeah.
ordinal is where in the order.
You got it.
Okay, I think I'm with you.
Now, when we start talking about infinity,
Yeah,
we're going beyond just counting.
okay.
We're entering a realm where things can get a little strange.
Oh, I'm all for strange.
All right, well, for starters, infinity isn't actually a single number.
Okay,
It's more of a concept
right.
that represents boundless amounts.
Okay.
And one of the first mind-blowing things you'll encounter is something called alef null.
Alef null. That sounds kind of intimidating.
It is. It's represented by the symbol euro, and it's considered the smallest infinity.
The smallest infinity.
No.
I thought infinity was just infinity.
Well, alef null represents the total number of natural numbers.
Okay.
1, 2, 3, and so on, forever.
Hold on a second. Isn't there an endless number of even numbers, too?
Yes.
And an endless number of odd numbers?
Sorry?
So wouldn't that mean there are more even numbers than natural numbers since every natural number has a corresponding even number?
You would think so.
Right.
What? It turns out in the world of infinity, all those sets,
Yeah.
natural numbers, even numbers, odd numbers, they actually all have the same size.
Wait, so you're telling me there's the same amount of even numbers
Yes.
as there are all numbers?
Yes, mathematicians call this cardinality.
How is that possible?
It's one of the first mind-bending concepts you encounter when exploring infinity. It turns out that adding one more element to an infinite set doesn't actually change its size.
I don't think I understand that.
Alef null plus
What?
1
Yeah.
is still just a alef null.
So we've got this infinite set, alef null, and it's way bigger than I thought.
It is.
But I have a feeling there's even more to this infinity story.
Oh, you're right to be suspicious.
Okay, good.
To go beyond alef null, we need to introduce the power set.
Power set. Okay, what is that?
Imagine you have a set with just two elements, the numbers 1 and 2. The power set of this set is a set that contains all the possible subsets you can make from those elements.
Okay, so we have a subset with 1, a subset with 2, a subset with both 1 and 2.
You got it. And one more,
What's that?
the empty set.
What's the empty set?
The empty set contains nothing at all.
Okay.
So the power set of 1 and 2 would be the empty set, the set of 1, the set of 2, and the set of 1 and 2.
So the power set is basically all the different combinations you can create from the original set,
Yes,
including the option of having nothing at all.
exactly.
Mm.
And here's where things get mind-blowing. The power set of any set is always bigger than the original set.
Okay.
And this is important. When we apply it to alef null, the set of all natural numbers,
I have a feeling things are about to get really weird.
a mathematician named Georg Cantor
Mm-hmm.
used something called Cantor's diagonal argument to prove that the power set of natural numbers is bigger than the set of natural numbers itself.
Hold on, so you're saying there's an infinity that's bigger than the infinity of all natural numbers?
It's more accurate to say there are different levels or sizes of infinity.
Different sizes of infinity.
To understand this, we need to shift our thinking from cardinal numbers
Okay.
to ordinal numbers.
Okay, remind me, what's the difference again?
Cardinal numbers are about how many
Right.
ordinal numbers deal with arrangement and order.
Okay, so ordinal numbers are like race positions, but on an infinite scale.
You got it. And the first transfinite ordinal we encounter is called omega.
Omega?
represented by the Greek letter.
Okay.
Think of omega as the next number after you've counted all the natural numbers.
So omega isn't about a bigger quantity, it's about a different way of thinking about infinity.
Exactly. You're picking this up quickly. Omega marked a shift in our perspective on infinity. It's not just about boundless quantities anymore.
Right.
It's about the way things are arranged and progress within that boundless realm.
Whoa. Infinity is so much more complex than I ever realized.
And we've only just begun to scratch the surface.
Okay, so we've got alef null, this incredible set of all natural numbers. We've
Yep.
got power sets that generate even larger sets.
Yes.
And we've got omega, this whole new way of thinking about the order and structure of the infinite.
You got it.
Where do we even go from here?
Well, this is where things get even more abstract. Mathematicians use something called axioms,
Axioms.
essentially fundamental assumptions,
Okay.
to explore even larger and more mind-boggling infinities.
So axioms are like the building blocks of mathematical reasoning.
Precisely. And one of the most important axioms for understanding larger infinities is the axiom of infinity.
So it just declares that infinity exists.
Essentially, yes.
Right.
It states that an infinite set, like the set of all natural numbers, actually exists. It might seem obvious,
Right.
but it's a crucial starting point.
So it's like we're saying, we know infinity is a thing now. Let's figure out what that means.
Exactly. And to go further, we need the axiom of replacement.
Okay, what's that one?
This axiom allows us to create new, larger sets by substituting elements within existing sets.
I'm not sure I follow.
Imagine taking all the ordinal numbers up to omega and replacing each one with omega plus that number.
So omega plus 1, omega plus 2.
Yes, and so on. We can even go a step further and replace each ordinal with omega times that number.
Omega times 2, omega times 3.
Exactly. And eventually omega times omega or omega squared,
Omega squared.
and we can keep going,
Okay.
reaching omega cubed omega to the power of omega and beyond.
So we're basically constructing a ladder of ever larger infinities.
Yes, using these axioms as our tools.
Wow. So is there an end to this ladder?
Well, even with these powerful axioms, there are concepts that hint at infinity so vast, they make everything we've discussed so far seem tiny,
Like what?
like inaccessible cardinals.
Inaccessible cardinals. Okay, that sounds ominous. What are those?
Imagine a number so large that you can't reach it by repeatedly applying power sets or any of the operations we've discussed to smaller numbers.
So it's like alef null. We couldn't get to alef null just by adding finite numbers together?
That's a fantastic observation.
So inaccessible cardinals are kind of like that, but on a much grander scale.
You got it. Just as you can't reach a left null through finite operations, you can't reach an inaccessible cardinal by manipulating smaller infinities. They exist on an entirely different level.
Whoa. This is making me rethink what big even means. We've gone from the biggest physical number we can represent on Earth to these crazy abstract concepts of inaccessible cardinals.
It's a lot to take in.
It is. I think my brain needs a break to process all of this.
We'll be back.
I can't wait to see where this deep dive takes us next. Stay tuned, folks. We'll be right back after a short break.
Welcome back.
All right, I've had a minute to process all that, and I'm ready to dive back into those inaccessible cardinals.
Excellent. So before we go any further, I think it's important to remember that these really big infinities rely on accepting certain axioms.
It's like we're saying, let's just assume these massive infinities exist and see where that takes us.
Precisely. And that brings up a really interesting question. Is math invented or discovered?
Yeah, because if we're just deciding that these infinities exist, are we creating them? Or are they already out there somewhere in some mathematical reality?
That's a question that has puzzled philosophers and mathematicians for a long time.
I bet.
But for today, let's focus on the consequences of accepting those large cardinal axioms.
Okay, so let's say we're on board with the idea that these inaccessible cardinals are out there. What can we actually do with them?
One of the most interesting things about them is that they behave like mini universes of sets.
Okay.
Inside each inaccessible cardinal, you have all the usual set theoretic operations, power sets, unions, intersections, but they're all contained within this larger inaccessible structure.
So it's like a whole world of infinity tucked away inside an even bigger infinity.
That's a great way to put it. And just like there are different sizes of infinity, there are different sizes of inaccessible cardinals. You have inaccessible cardinals, then larger inaccessible cardinals,
Okay.
and so on. It's a hierarchy of increasingly huge structures.
Okay, so let me see if I've got this straight. We start with an axiom that says this massive number exists even though we can't actually construct it.
Right.
Then we find out that within that massive number, there's a whole system of sets and infinities that behaves just like the regular universe of sets.
Exactly.
Then we do it again, finding even larger inaccessible cardinals that contain those systems and so on,
I
forever.
got it. It's a never-ending tower of infinities, each level containing a whole universe of mathematical structures.
So are mathematicians inventing these larger and larger cardinals, or are they discovering them? It feels like we're blurring the lines between creating and uncovering something fundamental.
It's a question without a definitive answer. Some mathematicians think we're discovering properties of mathematical reality, while others think we're constructing these concepts through axioms.
It really makes you wonder about the nature of math itself.
It does. And that's what makes this area of mathematics so interesting. It makes us ask big questions about the nature of math, its relationship to the real world, and the limits of what we can understand.
Well, we might not have a definitive answer to the biggest number question, but we've definitely expanded our idea of what big even means.
We've encountered different sizes of infinity, transfinite ordinals, power sets, and these incredible inaccessible cardinals.
It's a lot to think about.
It is, and it challenges our intuition at every step.
Definitely. And I have a feeling this is only the beginning. There's always more to discover when it comes to infinity.
You're absolutely right. The study of infinity is a journey without a final destination.
So true.
And there are always new and amazing discoveries to be made. It's a journey that constantly pushes the limits of human thought.
I'm feeling pretty intellectually stimulated right now, and more than a little bit in awe. This deep dive has really challenged my assumptions about numbers and the vastness of math.
That's what we're going for, to spark curiosity and a sense of wonder. Mission accomplished.
And to show just how beautiful and complex math can be.
Well said. So, is there anywhere else we can go from here? Have we reached the summit of this mountain of infinities?
There's always more to explore. For example, we could talk about the continuum hypothesis.
The continuum hypothesis. Now, that's a name I've heard before. Didn't someone say it was the most important unsolved problem in set theory?
It's definitely one of the biggest mysteries in set theory, and figuring it out would completely change how we understand infinity.
Okay, that sounds like a deep dive for another day.
It does.
I'm definitely making a note to come back to that continuum hypothesis, though. Sounds fascinating.
It is. But for now, let's shift gears a little bit. We've been talking about these really abstract concepts of infinity, but all of this has implications for how we understand the physical universe, too.
That's a good point. Sometimes it's easy to get caught up in the theory and forget that these ideas might have something to do with the world we live in.
So the question is, do these infinities actually play a role in the physical world?
Yeah, I mean, is there a connection? Well, whether or not inaccessible cardinals or any of the large infinities we've discussed have direct applications in physics or cosmology is still an open question.
So it's possible that these massive infinities are just mathematical ideas with no connection to the laws of physics.
It's possible.
Yeah.
But even if they don't have direct applications, the fact that we can imagine these structures, explore them, and reason about them logically tells us something important about human thought.
What's that?
It shows that we can go beyond the limits of our physical reality through math.
It's like we can look into another dimension where the rules of physics might not apply, and we can still explore it and make sense of it using math. That's pretty cool.
It is, and it brings us back to that question of, is math invented or discovered? If these infinities exist outside of our universe, does that mean we're discovering them or creating them through our mathematical systems?
It's a question that's been debated for centuries, and there may not be a simple answer.
Right.
But one thing is for sure. The study of infinity challenges our understanding of what's possible. It pushes us to rethink our assumptions about reality, math, and the limits of knowledge.
I agree. It's a humbling reminder that even with all our advancements, there's still so much we don't know about the universe.
So much to explore.
The study of infinity is a testament to human curiosity and our drive to understand the world around us.
This deep dive has really opened my eyes to how much is out there beyond what we experience every day.
And it's a reminder that the universe is far more vast and mysterious than we can imagine.
I'm feeling pretty inspired right now. This has been an incredible journey.
Me too.
We've gone from the biggest number you can physically make to the most abstract infinities. And we've seen how math can expand our understanding and challenge how we see the world.
We've learned that infinity isn't just one thing. It's a whole range of possibilities with different properties and implications.
And we've seen how powerful math can be. It can help us understand things that are beyond our physical reality.
It's been quite a journey.
It has. So as we move to the final part in this deep dive, we're going to bring things back down to earth a bit. We'll explore how these concepts of infinity relate to our understanding of the physical universe. What role, if any, do they play in the world around us? Stay tuned because the exploration continues. Okay, so we've spent a lot of time exploring this world of infinity. We've talked about different sizes of infinity, transfinite ordinals, power sets, and even those mind-blowing inaccessible cardinals. But now I think it's time to bring things back down to earth a bit.
Yeah, we've been deep in the realm of pure mathematics.
Right.
But now the question is, how do these abstract ideas, these huge infinities, relate to our understanding of the physical universe?
Exactly. We've been having fun with theory,
Right.
but do these giant infinities actually play a role in the real world?
Well, that's a question that's still up for debate.
Right.
Whether or not those inaccessible cardinals or any of the large infinities we talked about have any direct applications in physics or cosmology is something scientists and mathematicians are still trying to figure out.
So it's possible these massive infinities are purely mathematical constructs
Is
with
possible.
no connection to the laws of physics.
It's definitely possible. But here's the thing. Even if they don't have direct applications, the fact that we can think about these structures, explore them, and reason about them logically says something really important about human thought.
What does it say?
It shows that we can go beyond the limits of our physical reality through mathematics.
It's like we can look into another dimension where the rules of physics don't apply, and we can still explore it and understand it using math.
Yeah, and that brings us back to that big question we keep coming back to. Is math invented or discovered? If these infinities exist outside of our universe, does that mean we're finding them or creating them through our mathematical systems?
It's a really deep question, and there may not be one right answer, but I think what we can say for sure is that the study of infinity and those large cardinal axioms really challenge how we understand what's possible. They make us rethink our assumptions about reality, about the nature of math, and about the limits of what we can know.
It's humbling, isn't it? To realize that even with all our advancements in science and technology, there's still so much out there that we don't know.
This whole deep dive has left me with a sense of awe and a lot of questions. It's made me realize just how much is out there beyond our everyday experience waiting to be discovered and explored.
Absolutely. The universe is far more vast and mysterious than we can imagine.
And that's a pretty exciting thought.
It is. It's exactly what we hope to inspire in our listeners. A sense of curiosity and a desire to learn more.
So, as we wrap up this episode, I think we can say we've done something pretty remarkable. We've gone from talking about the biggest number you can physically build to the most abstract and mind-boggling concepts of infinity. We've explored how math can expand our understanding of what's possible and challenge how we see the world.
We've learned that infinity isn't just one thing. It's a whole spectrum of ideas with different properties and implications.
And we've seen how math can help us understand things that go way beyond our physical reality.
It's been an incredible journey.
It really has. So as we close out our deep dive into the world of infinity, we leave you with this final thought. What are the implications of infinities that exist outside our physical universe? Does this suggest that math is something we discover or something we invent? What other mysteries are waiting to be uncovered in the vast world of numbers? These are questions for you to ponder. Keep exploring, keep asking questions, and keep your minds open to the endless possibilities that are out there. Thanks for joining us.